We are looking at segment relationships today. We have two basic postulates for working with segments and links. And those are the ruler postulate, which establishes number lines, and the segment addition postulate, which describes what it means for one point to be between two other points. So starting with the ruler postulate, the points on any line or line segment can be put into a one-to-one correspondence with real numbers. So if you think about that with a number line, if you were to put a number line up against, say, this line segment here, then each of the points here would be assigned a particular number, and no two unique points, would have the same number associated with them on that number line. That's what this ruler postulate says. The segment addition postulate says if A, B, and C are collinear, then point B is between A and C if and only if the length of AB plus the length of BC is equal to the length from A to C. So B is only between these two if when you add the length of this one and the length of this one, and it gives you the length of the entire one. Alrighty, so we're going to use some of these in a two-column proof here. So our givens are Q is the midpoint of PR, line segment PR, and R is the midpoint of line segment QS. And they give us a picture to work with here. So I'm going to put in a few little notations on my picture. Since they tell me that Q is the midpoint of PR, here's PR, here's the midpoint, and that would mean that PQ and QR are congruent. And they tell me that R is the midpoint of QS. So R here is the midpoint of QS. So that would mean that this segment and this segment are congruent. I marked one of them with blue, and I used one tick for those, and then the other relationship I mark with two ticks. Now, just marking it on the picture there, I can see that means that QR is a part of both of these. And so if PQ is equal to QR and QR is equal to RS, then I could say that PQ would have to be equal to RS because they're both equal to the same thing. So what they're asking us to show is that the length of PR is equal to the length of QS. So PR, so from here to there, is equal to the length from here to there. Alrighty, so let's see if we can make that happen. Okay, in the proof, the first statement is a given, always. Now this time, instead of putting both given statements first, they split them up into two places. The reason for that is it kind of helps the flow. It kind of helps to see that this statement is a result of this one. And the number 4 statement here is a result of number 3. So Q is the midpoint of PR, line segment PR, that was given. So by definition of midpoint, we know that the length of PQ is equal to the length of QR, which is what we marked on the picture. They tell us also, given, that R is the midpoint of line segment QS. So again, by definition of midpoint, we can say that QR, length of QR, is equal to the length of RS. Now, because PQ is equal to QR and QR is equal to RS, then we could say PQ plus QR, which would be PR, is equal to QR plus RS, which would give us QS. That's by the addition property. That tells us that these two added together give you the full segment. Okay, now from that, we could also say PQ is equal to RS. Now this would be a result of using the second statement and the fourth statement and the transitive property. If PQ is equal to QR and QR is equal to RS, then PQ would equal RS. That's what that one says. Then the segment addition postulate allows me to say that PQ plus QR is equal to PR, and QR plus RS is equal to QS. So that's taking these two statements here and saying that because Q is between P and R, we can add them together, and that gives us the full statement there. Let me scroll. Okay, so finally, I can conclude from that, because PQ plus QR is equal to QR plus RS, that PR would equal QS by substitution. Okay, so you're going to try one of these. Here's a guided practice problem. There are 3 blanks on this one that you need to fill in. You're going to try it and then come back and watch the video and see how you did.